Okay, good afternoon, everyone. How are you doing today? Can everybody hear me?
Yes.
Okay, thank you. Okay, thank you very much. All right, so today I hope you all had a nice long holiday weekend. Today we're switching gears and we're beginning the topic of fluid statics. So just a little overview of what we're looking at this week. If we have a fluid where the particles are not moving past each other, they're not sliding past each other, there's no shear, what does the pressure at a point in that fluid look like? What does the pressure, how does it vary from point to point? And then if we further assume that the fluid is not moving, it's static, what's the equation we can come up with there? And we'll talk a little bit about this US standard atmosphere. Remember, now we're going really a deep dive into the concept of pressure. So what is pressure? If you remember from the introductory part of the course, pressure, if you think of this sort of imaginary idea of a fluid particle, it's the normal forces on the particle. So if you imagine the particle as a cube, there are normal forces that are, there are forces that are tangential to the plane, and there are forces that are normal to, excuse me, Chava, you need to, I'm very sorry. You need to go to Dad right now. Okay, I'm in the middle of my class.
Actually, she said that I can take a break.
Okay, go to Kathy, please. No, you cannot. You need to exit now or you're going to lose videos for tonight. Sorry about that. Okay. So anyway, pressure is the forces that are normal to the fluid particle.
I don't want to do this again.
Okay, so just a moment. Sorry, okay. So we're going to think about this concept of hydrostatics, pressure in a fluid at rest, with the introductory example of a giraffe. And let me just change my sharing. So I share my desktop. All right. So there's a YouTube video loading.
Time for a weekly trip to the new zoo.
Is everybody able to see the YouTube video?
Yes.
Okay, thank you.
Yep.
Awesome.
The giraffes. Good morning, Neil.
Hey, good morning. Well, if your blood pressure is up over the last night's elections, just think about these guys, okay?
Okay.
Now let's think about blood pressure in giraffes. Now, we kind of know we're about 120 over 80.
Right.
Guess what these guys are?
Let me think. I'm going to guess it's a lot higher because they got to pump the blood up that long neck to their brains.
Oh, hey, that's pretty smart. I'll tell you what it is. It's about 280 over 180.
Whoa.
Now,
that's mine after I have a show with Rachel in the morning.
It's all that coffee you drink.
There you go. See, that's there.
Oh,
But
hi.
I'll tell you. Well, now, okay, you see the head now. Now we're moving the head down. She's got the head down. This is Hodari. Now this is what is really, I don't know, I find really interesting is with giraffes, their circulatory system. You've got a heart in here that is about 25 pounds. Okay, very muscular, and it's got to pump all the way up about 6 feet. Well, what's interesting is all the way up through here, you know, they have a carotid artery. You know, like us, but this is about 6 feet. But what it is, it's real elastic. It's about an inch wide, and it balloons up. So that pressure from that heart, it can shoot that blood all the way up, and then it can also expand. Now, here's the problem. Now, all of a sudden, you drop your head down. If you put your head down and lift it up real quick, you know, you're going to feel dizzy. Yeah. Like, imagine with a giraffe, they have to go down and take a drink. Well, here's what they have to maintain that. Not only do they have the elastic carotid artery, but in the jugular vein, there's check valves. And that kind of stops the blood from flowing back so that they do not look at it like they're going to faint or anything like that. But then take a look at the feet. Now you think of gravity, right? Where's that blood going to go? You got an animal that's over a ton. You think the blood is going to pool in the feet. Well, if you're in the hospital, sometimes you have to wear those stockings, keep your blood up away from your feet from pooling there.
Mm-hmm.
Well, check that skin out. The skin is so tight on giraffes. Okay.
They have their own built-in compression socks.
Absolutely. And NASA has even done a lot of research on this. And also with their veins and arteries, they're not as elastic down below. And that they're a little bit harder, and they have muscles attached that'll pump the blood up. But here's another interesting thing that the head of NASA, when they're looking at anti-gravity suits, what they did find out too is when the young giraffes, before they're born, they have small arteries, of course, in their legs. And after they're born, they harden up. And the reason they do is if you have a hard arteries in there, you can't expand and you can't pool the blood. And their skin is tighter really than any other animal out there. And of course, their blood pressure, as we talked about, 280 over 180 is the highest blood pressure for any animal on Earth.
Wow, that's amazing stuff. Well, Neil, we have to leave you now. Are you going to still be with the giraffes next hour?
Yeah, we're going to be at the giraffes. We're going to talk about Zuri, how well she's doing. She's right here. And we're going to kind of show you her training because, like I said, she had lost one earlier in the year. A little one, and we were gearing up to hopefully she'll be successful in the future. We'll show you.
All right. So, so you saw that video, and you saw a video of a giraffe, and they said some interesting things. So hopefully you noticed a couple of those interesting fluid dynamics related things. I'm going to send you guys into breakout rooms. Sharing participants. Which for some reason, it's not giving me the option of breakout rooms for now. So let's just go ahead and have a discussion here in the main lecture. What were some of the interesting sort of physiological and fluid dynamics based things that you noticed when you were watching the video about the giraffe? Don't be shy. If you're feeling shy, you can put it in chat and I'll read it out.
They were talking about how down at the legs, the blood pressure would stay fairly high because the volume wouldn't expand at all in the arteries. But that was to keep it from pooling.
Right. Okay. Great observation. So really high blood pressure in the legs. And what do we think that that's due to?
The volume being constant, but more liquid trying to go there.
Right. Okay. Good observation. And then someone in the chat mentioned that the blood pressure will be high because it needs to pump higher distances. Did everyone notice when the zookeeper said that the giraffes, they have the really tight skin around their lower legs, right? As Noah was just mentioning. Did everyone notice that the zookeeper said that actually when they're in their womb, they don't have super tight skin, it's sort of regular tightness. And then after they're born, it develops and becomes really tight, right? Were there any other observations from the video? Remember the blood pressure that the zookeeper said that develops in giraffes. Does anyone remember the number? Yeah, about 280 over 180, right? And so what is that a typical? So 280 over 180, that's a systolic pressure over diastolic. So that's when, if you track the pressure in the aorta right at the exit to the heart in the largest artery, if you track it over time, over one heartbeat, one cycle, the highest pressure when the fluid is ejecting is a systolic pressure, and the lowest pressure is diastolic. So what is that typically in a human? You go to the doctor, if you get your blood pressure taken, you know, what are the values typically? Yeah, so then Abigail says 120 over 80 is normal for people, right? So 120 over 80 versus like 280 over 180, right? So huge, huge difference. So thinking about all those issues, let's go ahead and answer a couple of polls. All right, my poll that I created for today, here we go. All right. Okay, poll number 1. What do you think? Giraffes are not the largest animals on Earth, but the zookeeper mentioned that they have the highest blood pressure. Why? All right, we got 85% in. We'll keep it open for just a little bit more. All right, 95% of you have voted, so I'm going to go ahead and end the poll and share the results. So here's what you said, and all guesses here are perfectly fine because we haven't learned about this yet, right? We're just sort of using our intuition, what we think. So most people said that they're the tallest animals on Earth, so they have the largest vertical distance between their heads and their hearts, and that's the correct answer, as you will see a little later on the lecture. So we're actually going to do a fun giraffe example later. The other guess was, oh, well, they're narrow with a higher aspect ratio than something like a blue whale, so more pressure is required. That may be true, but the main reason is this second option here. It's the vertical height, because as you're going to see in a moment, in a fluid at rest, when we can consider that we're dealing with a hydrostatic situation, the only pressure difference is the vertical pressure difference due to gravity. Pressure does not vary in a plane. All right, and let us do another quick poll about the same giraffe problem. All right, it's about the tight leg skin, right? So the zookeeper mentioned that their lower leg skin gets really tight after they're born. Why don't they need that same tightness in the womb? What's your best guess? Again, you don't know the answer yet. You haven't learned it, but just with your intuition, why do you think that is? Oh, and the complete sentence for the first option got cut off. It's supposed to say, like they do after they are born. All right, I've got 95% in, so I'm going to end the poll and share the results with you. And just about everybody got the correct answer, right? So just like we talked about with poll number 1, if you're in a hydrostatic situation, you can consider the fluid to basically be at rest. It's the vertical pressure differences that matter. When the giraffe is in the womb, it's sort of floating around, it's on its side, it doesn't need the extra help pumping over great vertical distances. All right. So I'm going to move over to the tablet now and start on the next slide. I see I've got quite a few in the chat. Okay, great. All right, and I'm hoping that you are now seeing this slide, the title slide that says ESM 3234 Fluid Mechanics 1 in the annotator. Is that what you see?
Yes.
Great, thank you. All right, so talking here about pressure at a point. Now the cat's coming in, maybe she'll jump up and join us too. Okay, so the assumption that we're starting with here, we're not deriving an equation for any fluid dynamic situation. This is a fluid dynamic situation where the fluid particles, if you can imagine such a thing, are not sliding past each other. So no shear stresses are developing. That's the only assumption right now, okay? Now, we're considering this case of a triangular fluid particle, this wedge here, okay? And we're doing that to make a point. So we've got a triangular wedge and it's got a certain unspecified angle theta that this shaded surface on top, shaded in pink, makes, okay? We've got our X direction, Y direction, and Z is the vertical direction. And what we're doing here is we're adding up the forces on this element. It's submerged, it's floating in a fluid. And you can see that on each face on the XZ plane face, there's a pressure developing. And to get a force, we need to take the pressure acting on that face and multiply it by the infinitesimal area dx dz, right? Remember, we're trying to sum up the forces on each side. Same thing on all of the other surfaces. The X direction forces aren't shown just because the picture would be too crowded if they were. Then on the top surface, we've got the pressure with the subscript S, the pressure on that surface, times dx ds, because it's got an extent along the x-axis, and then it's got that S coordinate. And then on the bottom, we're showing the pressure in the Z direction times the area of that plane it's acting on here, dx dy. Okay, let me make a few notes about what things are here. So the P's with the subscripts are the average pressures on those faces. And what do we mean by those faces? So P sub S is the average pressure on the face labeled S. And of course, pressure has units of Newton per meter squared in SI units. Gamma is the specific weight. And that has units of force per volume, so newtons per meter cubed in the SI system. Rho is our density with units of kilograms per meters cubed. And then we have some accelerations that we're going to talk about in a moment. I'll just go ahead and write them here now, even though they're not written on the page yet. So A sub y is the acceleration in the y direction, A sub z is the acceleration in the z direction, and of course that has units of meters per second squared. Okay, so I'm putting down the units here because we want to think carefully about the forces. So we've got surface forces that are proportional to the surface area, so something with units of length squared, meters squared in this case. And so we've got surface forces due to pressure on all the faces. Because we've assumed that there are no shear stresses, we don't have any shearing forces, those would also be proportional to the area. And then we've got one body force. And does anyone know what that means, a body force? The definition of a surface force is that it's proportional to the area, to the size of the surface. Do you remember from physics what a body force means? Yes, so I've got a comment here. So it's proportional to the weight or the volume, right? So surface forces proportional to something that goes like length squared. Body forces proportional to something that goes like length cubed. Okay. All right, so we can show if we sum the forces in the y direction using Newton's second law, right? Just in general, the sum of the forces in the y direction equal the mass of the fluid element times the acceleration in the y direction. In this particular case, I'm not deriving it here because I'm trying to get through the slides. It takes a long time for some reason, teaching online, to get through slides longer than it does in person. I don't know why. But I'm going to do a similar derivation on the next slide, and I will go through it in detail. So take my word for it that the sum of the forces in the y direction can be written as the infinitesimal volume times the density over 2 times the acceleration in the y direction. And we can do the same thing in the z direction. Same thing, but of course now it's proportional to the acceleration in the z direction. Now if we take the limit as this fluid element shrinks to 0 till it shrinks to a single fluid particle, we can show something very interesting. We can show that the pressure that develops on the y face is the same as the pressure that develops on the sloped face in pink. And we can also show that the pressure that develops on the z face, the net pressure in the z direction, is the same as the pressure that develops on that sloped face. So what does that mean? Since theta is arbitrary, we can conclude that pressure is not dependent on direction at a point in a fluid, right? So if you take an object, you submerge it, you take, I don't know, a yo-yo and throw it into a tank of water, the pressure in the x direction is going to be the same as the pressure in the y direction, is going to be the same as the pressure in the negative z direction. Any direction you look at, the magnitude of the pressure is going to be the same. This is called Pascal's law. Okay, any questions about that? Just feel free to jump in at any time, but for now we'll move ahead to the next slide. All right, now we've looked at the pressure at one point and asked, does the pressure change depending on which direction, which side of the object I'm looking at? It doesn't. What about the pressure from point to point? What about if we have a larger fluid element and it's a pretty big difference? It's not an infinitesimal volume. It's a sizable difference from the bottom left corner to the top right corner. That's the situation we're looking at here. So now we have a cubic fluid element. And again, we've got the pressure developed. We're showing the pressure that develops on each face. And then in the middle, we've got the weight acting straight downwards. and that is denoted by the specific weight times the infinitesimal volume. So the difference between the last example and this one, this is still a small element, but we're not going to shrink as dx, dy, and dz go to 0. Okay. Now, I just want to point out something. The pressure is P at the center of this cubic fluid element. So when we go to the left by dy over 2, the pressure is P minus dp dy, the change in the pressure in the negative y direction, times dy over 2. Okay. Same thing on the other face. Pressure is P here at the center. If we move to the right by y over 2, then the pressure has a little bit added. It's P plus dp dy times dy over 2. Same in the z direction. And again, we're not showing the x direction forces just for clarity so that the picture is not too cluttered. All right, so now, remember, we're assuming that this is without shear stresses again. What we do when we say the pressure is P at the center of the element, and then we move half the cube to the right face, and then the pressure is P plus dp over y times dy over 2, what we're doing is really intrinsically using a Taylor series expansion, okay? So we can write the infinitesimal pressure that develops on the y face. We can just sum up the forces in the y direction. It's P minus dp dy, right, if we're looking on the left face, times dy over 2, times dx dz. How do I know I have to multiply by dx dz? Look at the units. Inside the parentheses, we've got something with units of pressure. We want a force. To get a force from a pressure, we need to multiply by area, right? So inside the parentheses, we've got units of pressure, and then outside, we need to multiply by the area of that face to get units of force. Minus, on the other face, we've got P plus dp dy times dy over 2 times dx dz, or if we combine those terms, we get dp dy times the infinitesimal volume. Okay, we can do the same thing in the x and z directions, and when we do, we find that the infinitesimal force in the x direction is minus dp dx, surprise, surprise, times the infinitesimal volume, and the same thing in the z direction. Okay, just check the chat box, nothing, great. Okay, so if we now add up all these surface forces in vector form, instead of looking at the individual x, y, and z components, we have now the vector surface force. Now this time, the S doesn't mean a particular face, the subscript S, it means surface versus body. It is the infinitesimal force in the x direction times the unit vector in the x direction, I, plus the force in the y direction times the unit vector in that direction, plus the infinitesimal force in the z direction times the unit vector in that direction. Or we can write it like this: dp dx in the I direction plus dp dy in the j direction plus dp dz in the k direction times the infinitesimal volume. And this quantity is del P, the pressure gradient. So in other words, a vector quantity that tells you how much the pressure magnitude changes in each direction. All right. So just a little bit about this del operator. You've probably seen it before in calculus. Just reminding you of the definition. It is a vector quantity. It's not a scalar. And its definition is that by the open round parentheses, I mean any quantity. You could put anything there, pressure, velocity, etc. It's d by dx in the I direction plus d by dy in the j direction plus d by dz in the k direction. So the resultant surface force can be expressed more simply like this. If we just rearrange that last equation on the last page. And you can see here, we've got a vector quantity here in the capital F. It's got a overline, which I mean to indicate vector. And over here, pressure is a scalar. It's not a vector. And it's not a vector because we just proved that it's the same in every direction, right? So it's just a scalar quantity. It does not depend on direction. But we've got a vector on the left-hand side. So we need a vector on the right-hand side. That's when you have to remember that, that del is a vector quantity. And my PDF annotator is just hanging up on me. Hopefully it'll come back. Come on, PDF annotator.
Oh, never mind.
Can you guys still see the PDF annotator, or are you just seeing that blue screen with the window?
Blue screen.
Yeah. Ugh. Okay. I'm afraid I'm going to have to quit the program and lose all my annotations and then reopen the file, unfortunately. Sorry about that. All right. Let's reopen that. Okay, here we go. Are you seeing the slides again in Annotator?
We can see it.
Great, thank you. And in the chat, I got a request to go back a slide and talk about the multiple lowercase d's with different subscripts. So let me just talk about that. I did lose my annotations, unfortunately, but I'll just re-annotate them after class and upload it a little later than usual. So what these multiple little d's are the infinitesimal extent in the x, y, and z directions, in the extent of the fluid element. So the fluid element is delta x long along the x-axis, and it is delta y long along the y-axis, and the same along the z-axis. Okay, so it's the length of the element. All right. So where we had just been was we had written this expression. So it's the resultant surface force in vector form per unit volume. And we showed that it was equal to minus grad P, the pressure gradient. And so let's just talk about these terms a little bit. So here is our sum of the surface forces due to pressure on our fluid element, our cubic fluid element. So in the X, Y, and Z directions. And then the denominator, we've got the volume of our infinitesimal little cube, right? We've got its length in the X direction, its length in the Y direction, and its length in the Z direction. And that's equal to the gradient. All right, now those are the surface forces, but we're thinking from the perspective of Newton's second law. We want to sum up all the forces acting on this element. The Z-axis is vertical, so the weight of the element, we write like this. I'm going to denote weight by capital W. And it's acting in the K direction. And it's equal to minus the specific weight, minus gamma, times the infinitesimal volume, so dx, dy, dz. So each of these dx, dy, dz has units of length, so in our case, meters. And I can see that the annotator has taken a little while, so I'm annotating, and then there's a few seconds lag between what I'm writing when it's showing up on Zoom. So it's the weight of the fluid element. Okay, so if we use Newton's second law in the general form, that's just the sum of the forces is equal to the mass times the acceleration. The deltas are there just to indicate that we're dealing with an infinitesimally small volume. We get the sum of the vector forces is equal to the surface forces and the weight, the infinitesimal weight, which is in the minus Z direction, which is equal to the mass of the element times the acceleration. Or we can write this. Now, if we just substitute in the expressions that we developed on the previous slides, we know that there are surface forces. If we look up here, we know that our surface forces can be written as the pressure gradient times the infinitesimal volume. So we can rewrite this as minus grad P times the infinitesimal volume minus now the weight. And the K direction is equal to rho delta X, delta Y, delta Z times A. Where's that coming from? That's the infinitesimal mass, right? So mass is density times volume. So we've got our density rho, and then we've got our infinitesimal volume, dx, dy, dz. So therefore, we can write this as all right, this is a really important equation. It's the equation of fluid statics, equation 2.8. I'll call it the hydrostatic equation. I'll even put a red box around it because it's super important to go along with our blue box there. So this is, remember again, the assumptions, we're still not assuming that the fluid is at rest. So maybe it's not, instead of calling it a hydrostatic equation just yet, let's call it just the equation for a fluid with no shearing stresses. Because we haven't assumed the acceleration is equal to 0. The truth is, in practice, we usually do assume that the acceleration is 0, but we haven't done that just yet. All right, I'm gonna hit save this time in case it crashes again. I've saved my work. Okay, now we're getting to the point where we can make the assumption that we are dealing with a fluid that's at rest, and we can start to answer and really look at, from a fluid dynamics perspective, the question of the giraffe, right? Why the giraffe needs such a high blood pressure. Okay, now we're taking that equation we just derived for a fluid with no shearing forces, and we're making an additional assumption that the fluid is at rest, so our acceleration is 0 in all 3 directions. Okay, so now that equation reduces to this simplified version. Del P minus gamma K is equal to 0. And this is the hydrostatic equation. All right, or if we write this out in component form, it would be dp dx is equal to 0, dp dy is equal to 0, and dp dz is equal to minus gamma. So we see that the pressure in a fluid at rest doesn't change in a horizontal plane, right? It doesn't depend on the x direction with the axes that we're using here, right? Where z is the vertical direction. Doesn't depend on the x direction, doesn't depend on the y direction, only changes in the vertical direction, okay? Because that's the case, we can now change this del p del z from a partial derivative into a full derivative, right? So this gives us dp dz is equal to minus gamma. That's equation 2.4. Okay, now it hasn't shown up yet for you guys, but you're going to see dp dz, there we go, is equal to minus gamma. Really important equation of hydrostatics. We haven't required gamma to be a constant. So this applies for incompressible fluids as well as compressible fluids. In the incompressible case, we're going to see this equation all the time when we're dealing with fluid statics. You're going to use it to calculate the forces that develop on a curved surface, a plane surface, underwater, you know, submerged. We're going to see it all the time in the coming weeks. In a compressible fluid, it turns out the specific weight of gases is very small compared to liquids. So dp/dz is not very large in gases unless you're dealing with really, really high distances. Question is, for the hydrostatic equation, isn't it plus gamma, not minus gamma? Excellent question. And I want to bring your attention over to these axes I have written here, right? And so on these axes, we're defining the positive z direction as up. So in the opposite direction as the gravitational force. So it depends on how you define your axes. In this definition, it's a negative. Okay. All right, let's wrap up. So for an incompressible fluid, we can just integrate again, being careful about our definition of our axes, and we get that del P is equal to P1 minus P2 is equal to gamma Z2 minus Z1. This is equation 2.5. Or you can write it in terms of depth. And then it's P is equal to P naught plus gamma H, where H is your depth. That's equation 2.8, and we're going to use this equation all the time. Okay, a note about H here in equation 2.8. You can think of H as the pressure head, right? So if you think about it, pressure is sometimes measured in units of length, which is strange. You go to the doctor and your blood pressure is read out in millimeters of mercury. That's because they used to actually compare the height. They used to actually compare the height of 2 columns of mercury, and the difference in the heights was your pressure reading. We'll see more on that later in the course. All right, for a compressible fluid, if you're dealing with large heights, then you can invoke the ideal gas law. That's equation 1.8 that we learned about a few lectures ago. You can combine that with equation 2.4, and you get dP dz is equal to minus gp over RT. Integrate it. And you end up with the following expression. Okay, you end up with this expression here. This is equation 210. Now, we can't finish the integration because we don't know what T is. Okay, but if we have an expression for how the temperature varies with height or depth, we can integrate it. And so that's why this naturally leads us to the example of the atmosphere. So I'm going to skip my cute giraffe example for now and finish up talking about the US standard atmosphere. And if we have time, we'll come back. Okay, so there's a thing called the US standard atmosphere. And it really was developed by scientists during this sort of golden era of rockets and flight because they wanted to be able to characterize the atmosphere in terms of height, in terms of pressure and temperature, right? Obviously, it's wildly variable, but they came up with a chart, tables that represent average year-round mid-latitude conditions. So here in the graph, you're seeing temperature on the horizontal axis and altitude on the vertical axis. And here we've got the layer from altitudes of 0 to 10 kilometers. We've got the layer closest to the Earth called the troposphere. Next, we've got the stratosphere. And you'll notice something interesting. In the US standard atmosphere, the temperature is basically a straight line in one layer of the atmosphere. So we can now take an expression for T. So here, for example, if we look at the troposphere, we can say that this is a straight line and it's equal to TA minus BZ, where TA is the absolute temperature at sea level. And beta is the slope, but it's called the lapse rate when we're talking about the atmosphere. If we now substitute that into the last equation from the previous slide, we get the natural log of P2 over P1 is equal to minus G over R, the integral from Z1 to Z2, dz TA minus beta times Z. And if we integrate that, we get P is equal to PA 1 minus beta Z over TA to the G over R beta power. So this is equation 212. PA is absolute pressure at sea level. So this is the equation for pressure in the troposphere, so the layer nearest to the Earth. And I'll just say that beta, TA, and G are all taken from table 2.1 in the textbook. And table 2.1 tabulates the properties of the standard atmosphere. And my goodness, it's time, it's 2:15, so I need to wrap up. In the top equation, yes, it's natural log of P2 over P1 in parentheses. I need to wrap up, it's 2:15, we're at time. So join Hyungan for his problem solving session on Friday, and I'll give him the giraffe problem. But long story short, giraffes need such high blood pressure because they've got to pump a very high vertical height. Danielle asks, will we get fully annotated PDFs? Yes, I'm going to re-annotate the earlier slides and post them. It'll take me a little longer than usual. Quiz 3, homework 3, due Sunday by midnight. Something that's come up, a few people have emailed me asking me if they need to complete these section homeworks. So there are some unpublished modules that you can see below the weekly modules. I'm working with tech support to get those removed, but no, you only need to complete the homeworks that show up in your weekly modules. Return the previous slide before I end the meeting. Yes. Okay. On Monday, Christine Burgoyne of the Engineering Communications Program will be visiting us to talk about the video project. And next week, we're going to talk more about hydrostatics and how to escape a car that is sinking. So 2 minutes over, I really apologize for that. You're free to go now, but I'll also stay on for a few minutes in case anyone has any questions. Thank you so much.
I want to ask you, do you know if there is a key answer for the problems in the book if someone you need to practice on these problems? So I look in the book, I cannot find the key answers. You know, if somebody need to practice, he needs to know the answer to know if he did it right or not.
Yes, there are practice problems in the book.
Practice, so they have, but they didn't have the answers.
Oh, they didn't have the answers. Okay.
Yeah.
Let me make a note for myself. It's possible that if I change a setting that that the answers will be available. But let me make a note to look into that. Thank you for bringing it up.
So, yeah, I mean the book, our book. So and you mentioned something about the homework problems are shown in 2 places. I didn't understand this.
No, yes, people were saying, so there are the weekly modules, which is all I want you guys to see and look at.
Yeah, yeah.
And those are published, but apparently you can still see some unpublished modules.
Yeah, I can see in the calendar, I see 2 homework or something like this. Is that what you're talking about?
Okay, I didn't even realize it's showing up in the calendar too. Yes, so you only need to do the homework 1, homework 2, homework 3, etc. that's associated with the module.
So yeah, I should only go to the week and solve whatever there.
Yes, and it's not simple to actually get those other modules to disappear, but I'm working with tech support, so they should be gone soon. I have another question. Could I upload the recording to Zoom from Zoom because my internet was awful? Yes, I actually always upload the recording. So if you go through the module to the page about today's lecture, there's going to be a link to YouTube. So sometimes it takes a couple hours to show up.
Thank you.
Anything else?
No, thank you very much.
All right, guys. Thank you so much. Have a great afternoon and weekend, and I will see you on Monday.